So today we start a new topic. I'll speak about Hilbert spaces. So we have X, a linear space, and it will be over the field K, which will be either the real number or the complex numbers. And on this space we will assume that there exists a scalar product which satisfies the following conditions. So let's assume first that the field is the real numbers. So this scalar product is a function from our field x to r, which is linear on both coordinates, which means that alpha x plus y z it's equal to alpha x z plus y z, and this for all x, y, z in x and alpha in r. It will be symmetric which means that x, y will be equal to yx. So you see that taking these two properties together, we get that the scalar product is also linear in the second coordinate. And then it will be positive, which means that xx, it's strictly positive if x is different from 0. Observe that by linearity, 0, 0, it's equal to 0. So this is in the case of the real numbers. We'll see that in the case of the complex numbers, these conditions are slightly different. Now, in the case in which X, it's a linear space over the complex numbers, we still have the same condition, which is linearity, which I recall it's, well, alpha x plus y z, it's equal to alpha x z plus y z. And this again for all x, y, z in x and alpha in z now. But the symmetry is replaced by the skew symmetry, which means that x, y will be equal to the complex conjugate of xy. So here, if a it's a complex number, so let's say that a is equal to alpha plus I beta, the complex conjugate of a, which will be represented by overline a, will be alpha minus I beta, and therefore we have, in the case in which the field is a complex, that the scalar product, it's not symmetric, but it's skew symmetric. And now observe that if you have x, y, alpha y, where alpha it's a complex number and x and y are elements of our linear space X, while by property B this is skew symmetric, so this means that this is equal to alpha y x, convex conjugate. Now by linearity this is equal to alpha y x, convex conjugate of that. Well, this is the multiplication of two complex numbers, alpha and the scalar product between y and x. So this is the complex conjugate of alpha y x, complex conjugate. And now we can use again b to write that this is the complex conjugate of alpha times xy. And therefore, what you observe is that, well, on the second coordinate, you don't have linearity, but you have Cesky linearity, right? If you have alpha multiplying y on the second coordinate, well, this is not linear anymore, but you have to replace alpha by its complex conjugate. And the last property remains the same. So you still have that if x is different from 0, then the scalar product between x and x, it's a real number and it's strictly positive. So these are the three conditions for a scalar product over the complex numbers. Now let's assume that you have X, the linear space. You have a scalar product which is defined on X, and say that we are working over the complex numbers, and we define a norm. So let's define on this space the norm of X as the square root of the scalar product of X with X. So this is a real positive real number. You're taking its square root. And my claim is that this defines a norm. So we have to check the three properties of the norm. So remember, the first property of a norm is that alpha x, it's equal to the absolute value of alpha times the norm of x. So let's check this. By definition, this is equal to the square root of alpha x. Now, by using the first property of a scalar product, we know that, well, this alpha goes out by linearity, and by Cesky linearity, we get here the complex conjugate of alpha. So what we get is alpha, the complex conjugate of alpha, times the scalar product of xx. Well, this gives you the absolute value of alpha squared, which gets out from the square root. And so you get that this is the absolute value of alpha times the square root of the scalar product of x, and this is alpha times the norm of x. So this is the first property. Then a second property, which was that the norm of x, it's strictly positive if x is different from 0. But, well, this follows from the third property of the scalar product. The norm of x, it's equal to the square root of the scalar product, and we have seen that the scalar product, it's strictly positive if x is different from 0. So that third property, that second property, it's obvious, and then we need to prove the triangle inequality, which means that we need to prove that x plus y, the norm of x plus y, it's less or equal than the norm of x plus the norm of y. And this, to prove the triangle inequality, we'll need a theorem, which I will state here, and then I'll prove. This is called the Schwarz inequality, and it says the following. Well, the absolute value of the scalar product between x and y, it's bounded by the norm of x times the norm of y for all x, y, and x. So in the next minute, we'll prove the Schwarz inequality, and then by using the Schwarz inequality, we'll prove the triangle inequality for the norm. So I left the statement of the Schwarz inequality, and we want to prove this inequality. Well, I can always assume that y is different from 0, because if y it's equal to 0, there is nothing to prove from this inequality, because by linearity you know that the scalar product of x with 0 is equal to 0. So this is 0, and this is less or equal than 0. So I can always assume that y is different from 0. Now let me take t a real number, and let's compute the scalar product of x plus ty with x plus ty. So this is equal, by linearity, well, this is x, then you have t yx plus t, it's a real number, so, well, when you take the complex conjugate, it's still t, plus t x y, and then we have t square yy. And we know, well, this is the scalar product of an element of x with an element of x, that this is always non-negative. So this is always non-negative, and I'll consider that as a function of t. As a function of t, it's a polynomial of second degree, which can be written as xx plus, well, by yx, we have seen it's xy, the complex conjugate of xy. So we get here that this is actually xy complex conjugate, and when you sum this with that, what you get is that 2 times the real part of this number xy. So this is equal to 2 times t, the real part of xy, plus t squared yy. Well, this is a real number. This is real. This is a real number. So this is as a function of t, it's a polynomial of second degree with real coefficients. And this is always positive. So this means that if you compute the delta, which is, remember, b2 minus 4 times ac, since this is always positive, this delta has to be negative, non-positive. And, well, here I want to get rid of this real and replace that by the absolute value of xy. So I will use here a slight trick. So xy can always be written as it's the absolute value of this complex number times some exponential I theta, where theta is between 0 and 2 pi. So what I will do is I will replace in this expression x by exponential minus I theta times x. Right, so I'll replace in these identities x by exponential minus I theta x. So here, by doing this, I get here, well, exponential minus I theta times x, exponential minus I theta times x, which is equal to, let me call maybe x hat exponential minus I theta x. So I get here x hat, and here x hat, which is exponential minus I theta x. By linearity, this is the real part of exponential minus I theta xy. but exponential, we've seen that xy, it's equal to the absolute value of the scalar product xy times e theta. So this is equal to the real part of exponential minus I theta, the absolute value of the scalar product of x with respect to y, exponential I theta. So this goes away with exponential minus I theta. And what I get is the real part of this absolute value, which is a real number. So this is equal to x, y, the absolute value. So what I just did is that, well, in this computation, by replacing x by x hat, which is exponential minus I theta x, where theta is chosen for this scalar product to be equal to this absolute value times that number, what we get is that instead of having here the real part of xy, we have the absolute value. So I will erase everything and just keep what we just obtained. What we obtain is that we have this identity in which we have, instead of x, we have x hat. And this is always non-negative. So as the polynomial in theta, what we get is that you see that we have 2 times the absolute value. So I get that 4 times x, the scalar product of xy squared, minus 4 times, here we have the scalar product of x hat with x and this is square. This is the norm square, times c, which is, again, y square. Now this is always, this is non-negative, I'm sorry. This is the delta. The delta has to be non-positive. And from that, we get that x, the scalar product of xy square, it's less or equal than x hat square times y square. And finally, let's observe that x hat square, which is the square root of the scalar product of x hat with x hat, but x hat is exponential minus I theta x, exponential minus I theta x, that this is equal by Cesky linearity, we get exponential minus I theta coming from this one, and then here we get exponential, the complex conjugate of exponential minus I theta is exponential I theta x x, and you see that this is equal to x squared. So I can replace here x hat, the norm of x hat squared, by the norm of x squared, and this is exactly the Schwarz inequality I claimed. So we proved the Schwarz inequality. Before we continue and we prove the triangle inequality, let me just add a remark. The remark is as follows. Assume that we have an identity here. Assume that the absolute value of the scalar of x and y, it's equal to the product of x, the norm of x with the norm of y. Then I claim that x, it's equal to alpha y for some alpha. So if we have an identity here, this means that, well, x belongs to the linear span of y, so that x is equal to some scalar times y. So let me prove that. And, well, we'll start again by the identity. So remember here, we had that x hat plus ty, x hat plus ty. We prove that this is equal to x hat square plus 2 times t times the scalar product of x with y plus t square, the norm of y square. So this was the inequality where x hat, it's still written here, is exponential minus I theta x. And we proved also that x hat, the norm of x hat, it's equal to the norm of x. So here I can replace x hat by x. So we have this identity, and now let's use the assumption that xy is equal to the norm of x times the norm of y. So this is equal to x squared plus 2 times t, x norm of y plus t squared y squared. And, well, and what is this? Well, this is the norm of x plus t times the norm of y squared. And this holds for all t. So I can choose t equal to minus the norm of x divided by the norm of y. So remember, I'm assuming y is different from 0. So I can take t as minus the norm of x divided by the norm of y. In this case, this expression here, it's equal to 0. So by choosing that t, I get that this expression is 0, and therefore I get that the norm of x hat, it's exponential minus I theta x. This is x hat plus t, y, but t, I chose t as the norm of x divided by the norm of y times y. Now this is equal to 0, right? Because this is the scalar product of x hat plus ty, and by definition this is the norm square. So we get that this is equal to 0, and since we've seen that the scalar product of a number, it's always positive, strictly positive, this means that if this is equal to 0, therefore that expression is equal to 0. And therefore this means that x, this implies that x is equal to exponential I theta, the norm of x divided by the norm of y times y. So this proves that indeed x is equal to a scalar times y, and this is what we claimed, right? And, well, this proves, so remember, I assumed here that alpha is equal to 0. If you get that, if you have, well, this identity, it's obvious for alpha, y equal to 0. So if y is equal to 0, you always get that this expression is 0, and this expression is 0. So there is nothing to prove. If you have that identity for y equal to 0, you can always, there is nothing, I mean, what I'm saying is that if you have this identity for some y different from 0, this implies that x is equal to alpha y, right? This identity doesn't say anything if y is equal to 0. So my remark, again, I insist on that, is that if you have that the absolute value of this scalar product is equal to this product for some y different from 0, then you can get that x is actually a scalar times y. So a second remark before we prove the triangle inequality is that you have also that the norm of x it's equal to the supremum over all y in x, y equal to 1 of the scalar product of x and y. So let's first prove that this supremum it's less or equal than the norm of x, and this follows from the Schwarz inequality. So you have that xy it's bounded by the norm of x times the norm of y by Schwarz inequality. So now if I take a y whose norm is equal to 1, this is equal to x, the norm of x, and therefore the supremum it's bounded by the norm of x. So this proves one inequality. And to prove the second inequality, so to show that the norm of x it's bounded by this supremum, we have to find one y which gives you the identity. So let me take y to be equal to x divided by the norm of x. Right? And here again, I'm assuming that x is different from 0, so that I can divide. If x is equal to 0, this identity is clear because, well, the norm of x is 0, and this supremum it's equal to 0 because all terms, if I take y scalar product with 0, this is always 0. So if x is different from 0, I can take y to be equal to x, the norm of x. The norm of y is equal to 1, so I'm allowed to use that element of x. And by using that element of x, what I get is that the scalar product of x, y, which is equal to the scalar product of x, x divided by the norm of x, by the Cesky linearity, this is a real number, so this is 1 norm of x scalar product of x with x, and, well, the absolute value of the scalar product of x with x, it's the norm of x squared, and from that I get that this is indeed x. And therefore, well, for that y, we get exactly the norm of x. Therefore, if I take the supremum it's larger or equal than the norm of x. So this proves the second inequality, and therefore we have this identity for all x. So in the previous remark, let me insist on that, we proved that the norm of x it's a supremum over all y with norm equal to 1 of xy. But we obtained one y for which this is an identity, so actually this is a maximum, right? So this supremum is actually a maximum, and that will be used later. Now we can go to the triangle inequality. So we want to prove that the norm of x plus y it's less or equal than the norm of x plus the norm of y. Well, the norm of x plus y, by definition, is the square root of x plus y in the proof of Schwarz inequality, we obtain that this is equal to, well, computed, so this is x plus 2 times the real part of xy plus y. The real part of xy, it's bounded by the absolute value of xy. So we can bound this by replacing the real part by 2 times xy, the absolute value of the scalar product. Now we can use Schwarz inequality to say that, well, this is bounded by x squared plus, so I have 2 times the absolute value, which I'm replacing by 2 times the norm of x, the norm of y, plus y squared. And this is equal to the square root of the norm of x plus the norm of y squared. And this is equal to the norm of x plus the norm of y. So this proves, indeed, that the norm of x plus y is less or equal than the norm of x plus the norm of y, and therefore that the norm defined by, if I define the norm of x as the square root of the scalar product of x with x, this is indeed a norm. Now I want to state and prove the parallelogram identity. So we've seen that x plus y squared, it's equal to x squared, norm of x squared, plus 2 times the real part of xy plus y squared. So if now I compute x minus y, the norm of x minus y squared, by the same identity, this is the norm of x squared, then I have 2 times the real part of x and minus y, but by linearity this gives me 2 times, minus 2 times the real part of x and y, and then plus the norm of minus y squared, but this is equal to the norm of y squared. And by summing these 2 identities, what I get, it's the so-called parallelogram identity, that x plus y, the norm of x plus y squared, plus the norm of x minus y squared, it's equal to 2 times the norm of x squared plus 2 times the norm of y squared. So this is the so-called parallelogram identity, and we will use these identities many, many times. Let me just define orthogonality. So if I take 2 points x and y in X, they are said to be orthogonal if x, y, the scalar product of x with y, it's 0. So 2 points, 2 vectors in X will be said to be orthogonal if their scalar product is equal to 0. And with that, let me use the space of the blackboard to define the Hilbert spaces. So a Hilbert space will be a linear space with a scalar product and if it has a scalar product, it has a norm, And it will be, so a linear space with a scalar product will be a Hilbert space if it is complete. Right, so if the space is complete with respect to the norm, and we defined already what a complete space is, so if it has a scalar product and if it is complete with respect to that norm, it will be called a Hilbert space. And this is the subject of this lecture and the next ones. So let me just remind this definition, because I will discuss this question. So I have X, a linear space, with a scalar product. This scalar product gives rise to a norm. So this linear space, which is endowed with this scalar product, is a Hilbert space if it is complete with respect to the norm. And complete with respect to the norm, I remind you, is that any Cauchy sequence with respect to that norm converge. So an observation. Well, consider sequence xn converging to x with respect to the norm. Right? So I'm considering here X, a linear space, which has a scalar product, and from that scalar product, we define the norm. So once we have a norm, we have a topology. So now let's consider a sequence xn converging to x. What I claim is that then xn, the scalar product of x and y, converge to xy. These are complex numbers, sequences of complex number, and what I'm claiming is that if xn converge to x in the space, then the scalar product converge. So the scalar product, it's continuous with respect to the topology generated by the norm. And well, this is obvious, and this comes from Schwarz inequality, because if I take the difference of x and y and xy, the scalar product, by linearity, this is equal to xn minus xy. And now if I use Schwarz inequality, this is bounded by xn minus x, the norm of xn minus s, times the norm of y. And this converges to 0 because xn is converging to x. So the scalar product, it's continuous with respect to the topology. Well, we have seen that once, so a second observation is that, well, assume that you have X, which is a linear space, and on this linear space we have a scalar product which induces a norm. Well, but assume that X is not complete. We presented a way in which we can complete the space X with respect to this norm. So let me represent by X bar the completion of X with respect to the norm. This is a larger space, and we know that this larger space, well, X can be embedded in this space, and X will be dense in this space. And what I want to do in the following minutes is to define a scalar product in X bar and show that these, now we have a space, X, which will be complete, that this norm will coincide with the original norm, the scalar product will coincide with the scalar product, the original scalar product, and therefore we'll have, well, this space will be a Hilbert space. So let me say it again. I'm starting with a linear space on which we have a scalar product. With this scalar product, we define the norm. And I'm assuming that, well, this space is not complete with respect to that norm. So now, once we have this norm, we have seen how to complete that space. So I'm calling X bar as the completion of X with that space. So we know that we can embed X in completion, and that X is dense. Okay. Now I want to show my claim is that this space is a Hilbert space. To do that, I need to define a scalar product in this space and then show that this space with the norm induced by the scalar product which I will define, it's complete. And this is the topic of the next few minutes. So here is our starting point. We are starting with a space which is a linear space on which we have a scalar product which is defined. From that scalar product, we define the norm. I'm assuming that this space with that norm is not complete. I'm representing by X bar its completion. And now what I want to show is that X bar is a Hilbert space. So let me I will define, the first thing to do is to define a scalar product. And to distinguish this scalar product from that one, I will represent with a double bar. So I want to define the scalar product x, y, double bar in X bar. So this is for X and Y in X bar. And the way we do it, well, we know that X, it's embedded in X bar and it's dense. So if X and Y belongs to X bar, I know that they exist. Xn converging to X, which means that Xn, it's a Cauchy sequence, if you wish, in X. And Yn converging to Y, Yn in Y. And I want to define xy as the limit of xn, yn. So there are many things I need to prove. The first one is that the limit exists. And the second is that, well, the limit does not depend on the chosen sequence. Of course, if I have here a sequence xn which is converged to x, I could have a second sequence converging to x, and I have to make sure that this sequence, that this limit will not depend on the sequence we chose. So let me first prove that the limit exists, then that the limit is independent of the chosen sequence. So to show that the limit exists, what I claim is that xn, yn is a Cauchy sequence. And this is a sequence of complex numbers, so if it's Cauchy, it converges. So I have to compare xn, yn with xm, ym. And for that, let me fix some epsilon positive, and I want to show that this difference, it's bounded by epsilon if n and m are large enough. Well, remember, xn is converging to x, so this is saying that xn, it's a Cauchy sequence with respect to the norm, the original norm. So I'll introduce in this expression the term xm, yn. So I add and subtract xm, yn, and I will first compare these two. So this is less or equal. Then, well, this term minus that one by linearity, it's xn minus xm yn. And then I'm comparing these two, and these two by linearity are equal to xm yn minus yn. Now I can use Schwarz inequality, so you see that Schwarz inequality will appear many, many times, to bound this expression by the norm of xn minus xm times the norm of yn. Since yn is a Cauchy sequence because it's converging to y, so this sequence is a Cauchy in the space X, we have seen that if we have a Cauchy sequence, the norm it's always bounded by a constant. So there exists a constant which bounds the norm of yn. And since xn is a Cauchy sequence, we know that for that chosen epsilon, if n and m are large enough, larger than n0, this is bounded by epsilon, so that would be bounded by epsilon times c0. We can repeat the same argument here. So we will have xm, which is bounded because xm is a Cauchy sequence, and we will have yn minus ym that will be bounded by epsilon, provided n and m are large enough. So that proves that indeed this sequence of complex numbers is Cauchy, and if it's Cauchy, it means that it converges, so that, well, we know, we have proved that these sequences converge. So this is the first step. Now the second step is, well, let's take another sequence, xn prime and yn prime, which are converging to x and y respectively, and let's prove that the limit is the same. So now I'm starting from two sequences, xn and xn prime, yn and yn prime. Xn and xn prime are converging to x, yn and yn prime are converging to y. So this means that, well, xn minus xn prime is converging to 0, and yn minus yn prime is converging to 0. And we want to see that these limits are the same. So we want to compare the limit of the sequence xn yn with xn prime yn prime. We want to show, we know that these two sequences converge. We want to show that the limit is the same, so we have to compare this difference. And we will proceed exactly as we did before. So we will introduce the terms xn prime yn. First compare this difference. So this difference is bounded by xn minus xn prime yn. And the second difference, it's bounded by xn prime yn minus yn prime by Schwarz inequality. So let me consider just the first term. The second is handled exactly in the same way. By Schwarz inequality, this is bounded by xn minus xn prime times yn, the norm of yn. The norm of yn, it's bounded because yn it's a Cauchy sequence. Xn and xn prime are converging to the same element, so this means that the difference is going to 0. So this is going to 0. And therefore, this limit does not depend on the chosen sequence. So this is, well, this is well defined. Right? For any x and y, we can find the sequence xn of points in x, yn of points in y, and we can define this scalar product as this limit. Now, what I claim is that this scalar product is linear, satisfies all the properties of the scalar product, and so this is the next step. So now we introduced this scalar product. My claim is that this defines a scalar product on the completion, x bar. So we have to prove the three properties. Okay, I'll just prove one of them, and I will leave the other three to you. So I'll prove that, say, this scalar product, it's sesquilinear. So what we want to show is that x alpha y plus z. So I'm taking x, y, z on x bar, and alpha as a complex number. And I want to prove that this is equal to alpha x, y plus x, z. Well, if x, y, and z belongs to x bar, so there exist sequences xn, yn, and zn in x, which are converging to x, y, and z respectively. And for that, well, so we know that if xn is converging to, if yn is converging to y and zn converging to z, this means that alpha yn plus zn, it's converging to alpha y plus z. And therefore, by definition, and I'm sorry, I forgot that I'm using a different notation for this scalar product. So what I'm really proving, what I want to prove is that this object is a scalar product. So for that. So by definition, since xn is converging to x, and alpha yn plus zn is converging to alpha y plus z, since in the definition of this scalar product we can choose any sequence converging, this is the limit in n of xn alpha yn plus zn. By the sesquilinearity of the scalar product in x, this is equal to the limit in n of alpha, the complex conjugate of alpha xn yn plus xn zn. Well, by linearity of the limit, this is alpha times the complex conjugate of alpha times the limit of xn yn, but the limit of xn yn, it's the scalar product of xy, because xn is converging to x, and yn is converging to y, and here also we have plus the scalar product of x with z. And this completes the proof of this identity, and as I said, the proofs of the other properties of the scalar product are obtained exactly in the same way, and I leave that as an exercise. So on x bar, we have a norm. So let me represent the norm with a triple bar, just to differentiate it from the norm defined in x. And this norm was obtained as the limit of the norms of xn. Now what I claim is that this norm, which was constructed when we completed the space x, this norm coincides with the norm that we get from this scalar product. So what I claim is that this norm x, it's equal to xx for all x in x bar. And this is clear because, well, how is this norm defined? This is the norm which was constructed in the completion. So we just completed the space. So this norm coincides with the norm of x for points in x. And it's obtained as the limit in n of xn if xn is a sequence converging to x of points of vectors in x. but this is the limit in n. Well, the norm in X is given by the square root of the scalar product. And this is, well, and this limit, it's equal to the square root of the limit, and the square root of the limit, it's what we define as the scalar product of X. So X bar has a scalar product. This scalar product is the norm of this scalar product. It's exactly the norm defined in X bar. So we have X bar. In X bar, we have a scalar product. The norm associated to this scalar product, it's the norm which we obtained by completing X. And we know that X bar is complete with respect to that norm. Therefore, X bar, it's a complete space with respect to the norm induced by the scalar product. Therefore, X bar, it's a Hilbert space. Therefore, if you start with a Hilbert space, if you start with a space with a scalar product, which is not complete, and then you follow the procedure of completion which I presented when we introduced normed linear space, we obtained at the end a complete space with respect to that norm. In this linear space, actually, we have a scalar product, and therefore, this space, this completed space, is a Hilbert space. So if you start with a scalar product, you proceed to complete the space, what you get, it's at the end a Hilbert space. So let me just, before we proceed, to point that out. So it's a remark which I should have raised before, is that, well, the scalar product we just defined coincide with the original one on the space X. So what I want to say is that if you take now X and Y in X, well, X and Y belong to X bar because X is embedded in X bar. So we have the definition of X and Y, the scalar product of X and Y, this new scalar product, and what I claim is that it coincides with the original one. And why is that? Well, because by definition, you're taking sequences xn, yn converging to x and y, but you can just take the constant sequence xn equal to x, yn equal to y, and therefore you get that the scalar product of x, y, it's equal to the limit of this scalar product, but well, this is constant equal to x and y, and therefore, when we constructed this new scalar product, well, this is just an extension of the original one. We are just extending this scalar product, which is defined on X, to X bar. So let's complete this lecture with some examples. Well, the first one, let's take some the space of continuous function, say in some interval AB. These continuous functions take values in the complex plane, and we define the scalar product of two functions, f and g, as the integral from a to b of fx, the complex conjugate of g dx. I leave it to you to check, well, that this indeed defines a scalar product, has all three properties, but this space is not complete. So I leave it to you as an exercise to show that this space is not complete, so you have to find a Cauchy sequence which does not converge, and the problem is that this Cauchy sequence will converge to a function which is not continuous. Then my second example, we've seen it already, so L2. L2 is the space of all sequence AJ, so J larger than 1. Here, AJ are, say, elements of the complex plane, And you require that the sum of the squares of the absolute values of the square is finite. So this is my space. We have already introduced LP, so now take P equal to 2, L2. We've seen that this is a linear space. And in this linear space, we can define a scalar product as the sum from j larger than 1 of aj times the complex conjugate of bj. And what I claim is that this defines a scalar product. I leave it to you to check. And now that this space is complete. So this is also an exercise. And actually, we proved that LP is complete for the norm. So the same proof applies here to show that L2 is complete. And my last example is, well, take D, a domain in RD. So domain, I remember, it's an open set which is connected. On this domain, you define by L2 of D as the space of functions which are measurable with respect to Lebesgue. So these are the functions from D, say, to R, which are Lebesgue measurable, and such that the integral over D of the absolute value of fx squared dx, it's finite. And on that space, again, you define the similar scalar product. So you define, let me write it here, fg as the integral over d of fx. Well, I'm assuming that they're taking real values, so I don't need to take the complex conjugate, such gx dx. So again, I leave it to you to show that this defines a scalar product. But now, this space, it's complete. Actually, this space is the completion of that one. So if you do the same thing, but instead of considering the interval AB, you consider a domain D, you define the scalar product on that space for, say, continuous functions. Take D to be a bounded domain. Otherwise, you have to assume that your continuous function have satisfied this condition. And that space, as I said, is not complete. Complete that space with respect to that scalar product, or the norm induced by that scalar product. And what you get is that this is its completion. So these are 3 examples, which will appear several times in the next lectures.